Yeah, I'm really excited to present my paper and share the stage with so many interesting takes on different scales for fabrication. As you said, I'm Daniel Campos-Zamora. I'm a PhD student, and I'll be presenting MobiPrint, a mobile 3D printer for environmental scale design and fabrication, which I did with Liang and my advisor, John Freilich. And before I dive into how we outline and define environmental scale design and fabrication, I want to start off with the conventional approach to digital fabrication, illustrated here and adapted from Stephanie Mueller and Patrick Bowdish's work. And we can see through this illustration that traditionally we think of digital fabrication as a way of scanning and making digital representations of individual objects that then we can make copies of and replicate. And we notice that this lacks context. For example, what is this key actually going to open, and how does it relate to the environment around it? And so our vision is to provide real-world context for fabrication and make machines that can relate to an entire environment and different objects in a space, essentially converting space into a printable 3D printable canvas using digital representations of entire scenes that we can then use mobile machines to go back into the space and directly augment, edit, the space with functional and decorative objects. So toward that vision, MobiPrint is a mobile 3D printer. So it's mounted onto a movable robotic base that uses LiDAR to scan, navigate, and traverse indoor scenes. And with a 3D printer that has been modified so that it can print directly on ground surfaces and provide functional objects, in this case, a little raised feeding bowl for my cat. And again, there's no guarantee that the cat will actually be as excited about the project as I was when I did it, but we'll come back to that later. And really, our vision is informed by three disciplines. And so even in this session, you'll see how HCI has constantly pushed digital fabrication forward and how we adapt definitions and ideas from robotics and architecture. So like I said, HCI has already explored, even in the last two talks, we see how we're pushing digital fabrication beyond the bounds of these static machines. And actually, it was at UIST in 2017 where mobile fabrication was introduced by TICE. In this case, imagining wearable 3D printers that allow on-the-go making. And in this scenario, they're making a tool for a bike that a part broke on their bike. So in this approach to mobile fabrication, you're really using the user to transport and make these machines mobile. But we kind of adapted the definition from robotics, where the emphasis on making machines that can locomote and traverse independently of a user to achieve and perform their desired tasks. And again, another shout out to Emily Whiting, who introduced the term environmental scale fabrication, in this case to reproduce a climbing wall by scanning and then selectively reproducing handholds on a climbing gym. And we kind of extend this definition and take ideas from architecture that focus on how we can extend this to large working areas as well. And so looking at these three different disciplines, we kind of set our goals for MobiPrint so that it can navigate, map, and print in ad hoc, meaning uninstrumented environments, essentially to convert a floor plan into a 3D printable canvas and enable a large working area. Again, kind of this idea of like big, small fabrication. I think we're taking it one step further. And so MobiPrint has like a 4-step workflow, and I'm going to go through each step and outline some of the decisions and challenges we faced at each step. I'm going to start off with mapping. Again, it's really crucial that we make a representation of the space that we can use as part of the design and fabrication pipeline. And so for this, we ended up really playing with a lot of different machines and exploring different options, and we ended up with a household vacuum robot. So I saw a lot of people at the demo session saying, is this like a Roomba? Technically, it's not a Roomba. It's a Roborock that has been rooted with like firmware that allows us to pull the robot state and information. And uses LiDAR, so it has a built-in LiDAR. In this case, I've removed the printer from the top to show the hardware. And with that LiDAR, we can actually use the map that it builds in the machine into our interface. And this is a little example animation of showing how it builds that map and give you a sense of how long it takes to map, in this case, my apartment. Next, critically, obviously, is you want to be able to choose the objects you want to augment your space with. And so for this, we have made a preloaded library with some models that we have printed and used. But we also have machine settings for process slicer that have been kind of optimized for the unique mechanical properties and sensitivities, frankly, of MobiPrint. So users can slice their own models and upload them as well. And so next, when you have that map as a design element and you have the objects that you want to print, we can kind of explore new ways of planning and editing the prints. And so now that we have this map as a design element, and users can treat the map as a canvas to place and edit their objects, we start to think of what operations make sense for you to be able to relate the 3D prints to the environment. And so we enable measuring, so you can kind of measure distances and place the object in precise locations where you might want them. And also be able to scale and rotate the objects in relationship to other things in your house or in your environment. So I have a little demo here of how a user might select a desired object. In this case, it's like a cane holder, and they might want to place it in a specific place, maybe near their table or work area, where they might rest it down and prevent it from falling over. And you see that once they have this map, they can kind of build relationships, measure distances, and use that as reference points for where they want to direct the MobiPrint to go and print it on the floor. And again, support some scaling and rotation in context. And once they're happy with their placement, they can direct the MobiPrint to go ahead and autonomously navigate to that location and print the object. And critically, of course, we have to be able to make a printer that can print on the floor. And so this involved modifying a cantilever 3D printer so that it extends out from the robot base, runs off a wireless board, it's completely untethered, and significant mechanical modifications to kind of keep the center of mass over the robot, again, to kind of help with the consistency and quality of the prints. And so what this allows us to do is to print directly on ground surface. In this case, I'm showing printed on a vinyl floor, but it can also print on carpet, for example. So again, tweaking the robot and tweaking 3D printers so that they can just work on arbitrary ground surfaces. And since we're doing some things that maybe 3D printers are not designed to do, we had to kind of make some new evaluations to see how this MobiPrint could function in different environments. So first, we just wanted to get a sense of how quickly MobiPrint could map out an environment. And so we tested 3 different setups. And we find that, again, these vacuum robots have kind of been optimized to work in these indoor environments, in this home environments. And so they map them out pretty quickly, within 12 to 15 minutes. But when you kind of give it a hallway or a classroom, it takes significantly longer because their kind of mapping algorithm doesn't really account for like having to go stop in a really long hallway, right? It's kind of look for these open spaces where it's trying to find the boundaries. Next, like I said, we're trying to print on arbitrary surfaces, so we had to really test the adhesion strength. I've never printed on hardwood, so we had to test that. And we printed these hooks and then used a force gauge to dislodge the print and measure how much force it took. In this case, in this video, it was 10 newtons to take it off the hardwood floor. And so we pretty much tested 4 surfaces, every surface I could find in my apartment, and then some, because again, these are not materials that you would normally print on in a 3D printer. And they're ranked here from strongest to weakest, and so I'll give a little bit more context, but we find that for carpet it adheres really well. Hardwood and vinyl also adhere 8.7 newtons and 37 newtons, so it adheres better to vinyl. And tile is NA because we couldn't get a successful print off the tile. We suspect that tile, despite it being relatively smooth and flat, which I thought would be make it a good candidate for printing, it dissipates heat too quickly, and so the plastic just doesn't adhere well to the ground or print bed in this case. And just to give some context of what I found to be a surprising test is printing on carpet. And so this is me trying to do the test, and I like this video because I think you can see my surprise / desperation when I realized that I might have just ruined the carpet in my house. So that was a little bit of I was not expecting that, so I had to explain that to my wife. And then further, we kind of went and tried to evaluate how accurately we can reach a destination, right? So we kind of built this test arena, 2 meter by 2 meter test arena, and then did a series of 20 targets, and then measured the offset to measure the error. And we found that the average error was 5.1 centimeters within this 2 millimeter space. So relatively accurate. but again, not quite, relatively accurate in relation to an entire environment, which is what we're trying to work across. And so having a better sense of what our system is capable of, we started to use this for some scenarios, and I just want to highlight a couple examples that we have. We identified 3 main use cases for accessibility, signage and wayfinding, and home furnishing. Obviously, all things that you would print on a floor. So the first one, and one that I think is most exciting to me, is the ability to kind of print tactile navigation aids that could be used for accessibility. In this case, we're printing this dot pattern or blister pattern tactile surface indicator, which can help people who are blind or have low vision navigate with a cane or with their sensations underfoot. And again, this is that cane holder that I showed in that video earlier on. Signage and wayfinding, again, kind of doing pedestrian navigation or just making decorative objects for, or graphic objects for like a conference. In this case, you might have seen this demo that I was printing yesterday, but also different signage to kind of guide people at an event. And lastly, it's home furnishing, again, different use cases that we've seen for traditional digital fabrication techniques. In this case, it's a decorative floral mural, an ergonomic footrest where we're actually able to print under the desk because it has a relatively low form factor. And we have a raised pet bowl, so I was actually able to get my cat to eat out of it eventually. But moving that, I want to discuss some limitations in future work for this. So one of the limitations that we are not printing on the move. We're doing this kind of park and print operations. And so for that, we would need to improve the hardware. Essentially, the motors on the Roomba are not precise. They're not stepper motors, right? They're really powerful, but they won't give you that precision. And on the flip side, the slicing algorithms, you would have to rethink of how you coordinate the movement of the robot and then the X and Y axes as well. We introduced some basic design operations, but there are more expressive tools you can build by allowing for patterning, different annotations. And we can only store one map at a time, and we can't share that environment with different machines. And so future work would explore how you can support multiple maps and also multiple robots as well. And I just want to end by talking about some design considerations for future mobile and environmental scale fabrication, where I think there's some exciting opportunities and overlap with work at UIST that kind of emerged after we reflect on our prototyping process. The first one is integrate the environment and context information into the design process. And here we use a floor plan as like a design element, but you could also do 3D representations of objects as well that you can scan in. We kind of went all the way in for automation, so trying to make the robot completely autonomous and navigate spaces independently. But we've seen work at UIST on interactive kind of turn-taking fabrication as well. I think it's really important to kind of push the boundaries so the machines can interface with real-world objects, not everything that you can bring into a 3D printer. And personally, something I consider really exciting is that once you have this different relationship with the environment, you can really think of how permanent should these objects, how long should they last? And I think there's good overlap with a lot of work I've seen recently on designing for decay or some organic growth where the object evolves or decays over time. And so I think there's a lot of exciting opportunities in this community as well, and just looking back that I think the community could tackle. But with that, I'm happy to take any questions that you may have. Thank you.
Thank you so much for the very cool presentation. I really like this work. Marwa from MIT CSAIL. So you mentioned how there are like limitations in terms of surfaces that you can print on. I was just wondering if you also considered ways to modify these existing surfaces to make them like more easy to print on, or modify like the amount of force that it takes to remove a part from them.
Yeah, beyond, I think like bed adhesion is generally a problem that people have with 3D printing, right? So like tweaking like your first layer properties, the geometry, your brims and stuff, that's stuff you can do. But we have, I don't know if I thought about editing the surfaces, but I almost thought of how I can prep the surfaces. And so for example, I do have clearance underneath the robot. So if you wanted to, you could put a heated, like you could almost put the heated bed, right? So that it heats the floor a little bit, and then the robot kind of heats the floor a little bit, moves forward, and then prints. Right? But again, for this iteration, you have to take into account the power consumption. Once you add another heating element like that, then you're going to need a much bigger battery. And we found that at least by using PLA, which is kind of forgiving and you don't need a heated bed all the time, that we were still able to get some prints off.
We have time for one more question.
My question is, what can we choose? For now, we can see it's basically on the ground, on the flat surface. Can we choose
I think with like robotic arms, for example, you kind of have like mechanically you can have a different axis. I think I haven't printed sideways or upside down, but I know that probably involves different parameters for the slicing of the models. But I think it's something that we definitely discuss in the paper as well, ways that you can kind of add other dimensions in which you can print.